Hey everybody, welcome back for our second episode of our AP review topics. And today's topic is all about continuity. And when we talk about continuity, I think that to kind of go back to the basics, think of continuity simply as just a smooth curve with no breaks, no jumps. If I'm writing with my pen, I never have to pick it up. That's continuity. I think more importantly for us and for our ability to make strong mathematical justifications and explanations, we need to understand the mathematical conditions for continuity. So I want to begin with something we talked about in the previous lesson, which was this. If the limit as x approaches some value a from the left is equal to the limit as x approaches some value a from the right, then the limit exists at that point. That was a key mathematical written justification for a limit existing. In order for a function to be continuous, though, we need to expand on this definition. Because remember from last time, the limit could exist at a hole. A hole is clearly not continuous, right? That's a break in the graph. So the third piece of this is that that limit must also equal the value of f of a function. So this is an easy way to sort of remember what it takes for continuity to happen. The limit must exist and then be equal to the function at that point. So we could also say we know a function is continuous and the limit must also exist. So what are some different points of discontinuity? What are some different types of discontinuities that you might see? The first, let's talk about the jump. And in a jump discontinuity, the limit does not exist because the graph will jump at some point, where the limit from the left and the limit from the right are clearly different. The second type is an infinite discontinuity. And these are most commonly referred to as your vertical asymptotes. Maybe it looks like that. Then the final one that I want you guys to really know well is the removable discontinuity. Now, removable discontinuity are simply holes in the graph. Could look like this, or maybe a piecewise function has defined a new point for f of a, down here, up here, wherever, but still discontinuous nonetheless and referred to as a removable discontinuity. But remember here, the limit exists at a removable discontinuity because it's still approaching the same value from the left and right. I would know all these by name and be able to explain and what's true about each one of them. Okay, let's move into a problem. And this is a certain type of problem that I like to do anytime we talk about continuity algebraically, like what it could look like. And those are piecewise functions. So I'm going to give you an example of a piecewise function here. And we're going to prove that this function is continuous at a point. So let's say that f of x is equal to x squared plus x for all values of x that are less than 1, and then 2x for all values of x that are greater than or equal to 1. And I want to know, is f continuous at x equals 1? And then I also want to justify that, justify why it's continuous at that point. All right, so what we're going to look at are the two one-sided limits. I'm going to begin with the limit as x approaches 1 from the left. And in a piecewise, that would be the part that is obviously less than 1, the first part of this piecewise. So if we substitute 1 into the top part of this piecewise, we're going to get 2. Now we're going to do the limit as x approaches 1 from the right of f of x, which is going to be from the bottom function, but this is also equal to f of 1, and it's going to take on f of 1 because of the equals to part of our inequality. So now, with an easy plug-in, we just have 2 times 1, which is 2. Because those are the same, we know that it is continuous at that point, so therefore, is f continuous? Yes. And easily can justify this because the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the right of f of x, which is equal to f of 1. Very simple and supported by our work that we have up above. Okay, one last thing with continuity that I want to touch on is an important theorem that is a result of continuity. We're going to, should all remember this one, the intermediate value theorem. Most commonly referred to as IVT. Intermediate value theorem is very simple to understand. Let's say you have a function. So if f of x is continuous, it's got to be continuous, on a closed interval from a to b. So let's say we know f is continuous. If it's not, you can just throw this right out the window. It does not apply. Got to draw a graph. Okay, so here's a. Let's say this is b. And let's say your function, it could look like anything, right? Let's say it's going to go from here to here. Maybe it looks like this. So what the intermediate value theorem says is that because this function is continuous, as we go from a to b, this graph will pass through every y value between f of a and f of b, right? It's going to go through all of those points. So every value between f of a and f of b will be included in the range over this domain from a to b. I think when we get really into the mathematical writing of it, they say let there be some point c, and f of c is there's every value between f of a and f of b. But just remember, it's going to go through all the points, right? Every point between f of a and f of b will be passed through over this domain. The graph could go outside of that range, but this is what we can say for sure, is that it will go through all of those. So if we do just a really quick example, I want to put some numbers on this thing. Let's say I tell you that a continuous function f takes on the values f of -1 is equal to 5, and f of 3 is equal to -2. And anytime I have points, probably a good thing to start with is to just draw a graph, right? What does this thing look like? So f of -1, 1, 2, 3, 4, 5, right there. And then f of 3, 2, 3, 1, 2, down here. So we know, based on what I told you, is that this graph is continuous from this point here down to this point here. We don't know, does it go straight? Does it curve? Does it go way high, way low? We don't know, right? But all we know is that it's got to go from here to here and be continuous over the interval. So I'm going to ask you just a series of questions to think about. Is there a point C such that f of c is equal to 2? Yeah, definitely, right? Y equals 2, that's right here. It's got to pass through y equals 2, right? At some point, we don't know where, but there will be a point where it's going to pass through y equals 2, so that one's good. Does f have a 0? Does it pass through a 0 on this interval? Yeah, it does. It's got to cross over the x-axis. It's got to go through y equals 0 at some point. Is there a point such that f of c is equal to 6? That's up here. There could be, but there doesn't have to be, right? This goes into that whole, is it must be true, it could be true, right? There could be a point. We don't know for sure. All we can say for sure is that it will pass through every point between here. That's a good overview of the IVT, and then an extra example. As always, guys, if you want to talk about anything else with continuity, just let me know. And I'd be happy to give you guys some more information. But until next time, keep up the good work and happy studying.